Let's do some triple integrals now. So, as a brief overview, if the domain of integration is a box in 3D, so x is between a and b, y is between c and d, and z is between, let's say, e and f. Then the triple integral over e of a function f of x, y, z, dv. dv is the volume element, which is in rectangular coordinates, is dx, dy, dz, or depending on the concrete use, any permutation of dx, dy, dz, which are 6 of them. So this integral can be calculated by as an iterated integral by Fubini theorem by integrating the three variables in order. So integral. Let's integrate x first. So like we discussed before, the process goes from inside out. If I integrate x first, a to b f of x, y, z, dx, then y second, c to d is the initial integral, dy, and e to f dz. So again, to understand it, we proceed from inside out. So first we do this, and after we integrate the x variable, this depends on x of y and z only. It depends on y and z only. Right. Then after we integrate the y variable, depends on z only. Right. And then finally we integrate the z variable, we get a number, and this number is the triple integral over the box T of the function f of x, y, z. But here we integrated x first, y second, z third. We can do 6 combinations of this, and all of them produce the same answer, maybe the triple integral over the solid E of the continuous function f of x, y, z, dt. Okay, so let's try to take a concrete example. Let's say P is the following box. X is from 0 to 3. Y is from 0 to 2. And Z is from 0 to 1. So let's calculate the triple integral over this E of the function x plus 2y plus 6z dv. X plus 2y plus 6z dv. And let's make the choice that to integrate z first, y second, and x third. Okay, so let's try to start. So this will be integral. Z first, we have to do integral from 0 to 1, then on the outside, integral from 0 to 2, and integral from 0 to 3. So z first, y second, x third. X plus 2y plus 6z, dz, dy, dx. Okay, so let's do the inner integral. Okay, so this will be xz plus 2yz plus 3z squared between z equals to 0 and z equals to 1. That means x plus 2y plus 3. X plus 2y plus 3. So we got the double integral. So the triple integral reduced to a double integral after we integrate one variable out of 3. So we get integral from 0 to 3, integral from 0 to 2, x plus 2y plus 3 dy dx. Okay, so let's try to calculate the inner integral now again. So this will be integral from 0 to 3 times xy plus y squared plus 3y. So xy under derivative of x plus y squared under derivative of 2y plus 3y under derivative in terms of y equals 3 between y equals to 0 and y equals to 2. Then dx. But y equals to 2, so this will be integral from 0 to 3. If y equals to 2, we get 2x plus 4 plus 6 plus 10 dx. So again, progressively we got from 3 variables to 2 variables to 1 variable, and we got a normal integral of like in calculus 1. So this will be integral, it will be x squared plus 10x between 0 and 3. Value of 3 is 39. Value of 0 is 0. So this will be the result of the numerical problem. Okay, so it's pretty clear what how to integrate over boxes by using Fubini theorem 3D version. Again, let's mention the simple case of separable over rectangles, a three-dimensional version. So note S of R 3D version. So if E is a box, so X is from A to B, Y is from C to D, Z is from E to F, then the triple integral over such a box of a product of a function of x times a function of y times a function of z. That's why it's called separable. So let's try to give some names. I can use A again. So alpha of x times beta of y times gamma of z dv. So we got separable over rectangles in 3D. So that's a separable function. Separable means a product of a function depending on x times a function which depends on y only times a function which depends on z only. So in this case, separable over rectangles gives us integral from a to b f alpha of x dx times integral from c to d beta of y dy times integral from e to f gamma of z dc. So in case we integrate a separable function over a box in 3D, it immediately splits into a product of three simple integrals as in calculus 1. Right? So okay, so let's try to complicate our life a little bit. So let's find how to do integrals over domains that are slightly more complicated than boxes in 3D. So let's do triple integrals over domains that are simple with respect to one of the coordinate axes. So triple integrals over domains that are simple with respect to WRT, one of the coordinate axes. Let's try to choose the z-axis. Triple integrals over domains simple with respect to the z-axis. Simple with respect to the z-axis. What what is such a domain? So, okay, so let's try to sketch the idea of such a domain. So for such a domain, we are given clearly, so this domain E, we are clearly given that when it comes to the x and y coordinates are in a definite plane domain D. So xy, the point xy belongs to a domain D, which is specified in the problem. Okay, so let's say this is a domain D. Let's assume this is domain D. So that's a domain containing the variables x and y only. Now, for every xy, the point x, for every xy in D, the z coordinate is between a lower surface and an upper surface. So let's say this is a lower surface. So this altitude, let's call it low of x and y, and the other altitude, let's call it q of x and y. So basically, we have above the domain D, imagine above the domain D, we have two surfaces, a lower one and an upper one. So above the domain D, we have a lower surface. So this surface is z equals to low of x and y, and the upper surface and this upper surface is z equals to u of x and y. So what's the formal definition of such a domain simple with respect to the z-axis? xy is confined to D, D is a plane domain in 2D, and then for every point xy in D, z is between low of x and y, lower, L from lower, and smaller, less than or equal u of x and y, u from the upper surface. So this stable intuition of the domain D, there's a domain between this lower and upper surface. Okay. How to do triple integrals over such domains? So let's assume that E is defined like this. I have to be zoom in like this. xy belongs to D, and z is between low of xy and upper of x and y. Okay, so what will be a triple integral over E of a function f of x, y, z, dv. Domain which is simple with respect to the z-axis, right? Because the z coordinate is between a lower and upper, right? So if we, similarly, we can define domains which are simple with respect to the y-axis or simple with respect to the x-axis. Okay, so the technique of calculating such integrals is to reduce to a double integral. So reduce to a double integral. So how to do this? As we discussed before, the process is from the inside out. So the last we'll do is a double integral. So double integral over what domain? It's kind of pretty obvious from we can guess. The best guess would be double integral over D. Right. Of what? What's the inner integral? Integral from lower to upper. Integral from low of x and y to u of x and y. F of x, y, z, dz. So what happens here? We integrate the z variable from a lower limit to an upper limit, and the lower and upper limits also depends on x and y only. So after we perform this integral, this inner part will depend, so this depends on x and y only. Then we got a function which depends on x and y only, defined on a plane domain D, and we know from previous work how to do double integrals. So we got double integral over D. This function depends on x and y only, dA. So the idea is the process of reduction. Instead of calculating the triple integral, we reduce the calculation of the triple integral to a double integral by first integrating to z the integral. Okay, so that's the general principle, and let's start to give an example. Start with an example. So let's see, d is the following. Let's say x is between 0 and 1 is and y is between 0 and 1 is like a square. So this will be d. And then z is between, this is the lower surface paraboloid, so z is given or equal to x squared plus y squared. And well, let's see, if x is between 0 and 1, y between 0 and 1, always x squared plus y squared is less than 2, right? So let's put 2 as the upper surface. So that is sorry, not D. That is the solid domain E. The solid domain E is a base, which is square base, right? It's a base in which both x and y variables are between 0 and 1. On the lower surface, the paraboloid z equals to x squared plus y squared, and the upper surface is just horizontal plane, z equals to 2. So above a square base between a paraboloid and a square and a plane. How to find that? So we need a, let's see, triple integral over E. Let's take a simple integral of, let's see, z dv. So again, E is above this square, the unit square, between the paraboloid z equals to x squared plus y squared and the plane z equals to 2. Okay, so let's solve this problem. Triple integral over E of z dv is, let's reduce everything to a double integral over the square 0, 1 cross 0, 1. So double integral over d. We can put dA in front just to make sure that we got it. So integral from lower x squared plus y squared to 2 of z dz. Right? So this will be double integral over d dA, then z squared over 2 vertical bar between z equals to x squared plus y squared and z equals to 2. Okay, so this equals, let's put a constant out of the integral, so it's 1 over 2, double integral over d. Now let's put d as equal to 8. Z squared between x squared plus y squared and 2. Value of 2 is 4. Value of x squared plus y squared, we are looking at the z squared. 1 over 2 was already taken in front of the integral, so only z squared matters here. 4 minus x squared plus y squared squared. So minus, what's x squared plus y squared squared? Minus x to the power 4 minus y to the power 4 minus 2x squared y squared. Right? From, okay, so this is this difference. Right? Okay, so we get 1 over 2, integral from 0 to 1, integral from 0 to 1. Let's integrate the x variable first. So 4 minus x to the power 4 minus y to the power 4 minus 2x squared y squared dx and then dy. Dx and then dy. Equals 1 over 2 times integral from 0 to 1. Okay, so let's do the integral with respect to x. For x minus x to the power 5 over 5 minus xy to the power 4 minus 2x cubed over 3y squared minus 2 over 3 x cubed y squared between x equals to 0 and x equals to 1, and then dy. Okay, kind of running out of space here, so let me erase some previous work. Okay, so let's see. And start from here. This equals 1 over 2 integrate from 0 to 1 of what? So when x equals to 1, we'll get 4 minus 1 over 5 minus y to the power 4 minus 2 over 3 y squared when x equals to 0, we get a 0, and then we get dy. And that will be 1 over 2 times 4 minus 1 over 5 is 19 over, so integrate from 0 to 1. 19 over 5 minus y to the power 4 minus 2 over 3 y squared dy, which is 1 over 2 times 19y over 4 over 5 minus y to the power 5 over 5 minus 2 over 9y cubed, vertical bar from 0 to 1, and that will be 1 over 2 times 19 over 5 minus 1 over 5 minus 2 over 9. And that will be 1 over 2 times 18 over 5 minus 2 over 9, which is 1 over 2 times 9 times 18 is 162 minus 10, 152 over 45. Then we simplify 2 is 152, we get a 76 here, and the final result will be 76 over 45. So that's how we do triple integrals over domains are simple with respect to one of the coordinate x.